Hello, this is one of a series of videos on the AQA A-level Chemistry Paper 3 or 74053 component. This one's specifically focusing on the 2020 paper. I'm going to be talking through each of the multiple choice questions in that paper and explaining how to arrive at the answer. When you're going through the mark schemes from AQA, it will tell you what the answer is, but there won't be an explanation as to how to get there. The likelihood is if you're watching this video you will want to just find the answer or explanation to one specific question. So there are timestamps in the video, you can navigate to the specific question you want to find. So starting off with question number 7. When heated, a sample of potassium chlorate KClO3 produced 67.2 centimeters cubed of oxygen, and it tells you the temperature and the pressure. What's the amount in moles of potassium chlorate that has decomposed? So starting off then, we're told the volume of oxygen, we're told the temperature and the pressure. So in your mind you should be thinking this is going to be the ideal gas equation, PV/nRT. We're being asked to find the moles of potassium chlorate, which is KClO3, it tells you in the question. And you're being told the volume, pressure and temperature of oxygen. So firstly we're going to need to work out the moles of oxygen. So how do you work out the moles of oxygen from the ideal gas equation? Well, you rearrange that to get PV over RT. Now remember, here we have to use SI units, so pressure is 110 kilopascals or 110,000 pascals. The volume, 67.2 centimeters cubed, has to be converted to meters cubed. So centimeters cubed divided by 1,000,000 or times 10 to the minus 6. So pressure times volume, pressure in pascals, volume in meters cubed. R is 8.31 and the temperature is in Kelvin already. So plug those numbers into your calculator. The moles of oxygen you get are going to be 2.985 times 10 to the minus 3. So it's asking us the moles of potassium chlorate though, so we're not quite finished there. We need to work out how to get to the moles of KClO3. So oxygen to potassium chlorate is a 2 to 3 ratio. Sorry, 3 to 2 ratio. So if the moles of oxygen is 2.985 times 10 to the minus 3, we need to divide by 3 and times our answer by 2. That will give us the moles of KClO3 being 1.99 times 10 to the minus 3. Or answer B. Question number 8, which has a bond angle of 109.5 degrees. So going through each one of these, you have diamond. Diamond has carbon containing 4 bonds per atom, 4 bonding pairs, so diamond does have a bond angle of 109.5 around each carbon. Graphite, each carbon has 3 bonding pairs, and the extra electron in carbon becomes delocalized and moves between layers. So graphite has 120 degrees as its bond angles around each carbon. NH2 minus, so nitrogen is in group 5, so it's going to have 2 bonds to hydrogen. It's going to have 2 lone pairs. I'm just going to draw that extra electron as a cross. It's got a negative charge. So NH2 minus has 2 bonding pairs, 2 lone pairs. The bond angle would be 104.5 degrees or thereabouts. And finally NH3, you've got 3 bonding pairs, 1 lone pair. The bond angle is going to be 107 degrees there. That would be a pyramidal shape. So diamond is the one with the bond angle of 109.5. Question number 9. Which reaction has an enthalpy change equal to the standard enthalpy of formation of silver iodide? So remember the definition, key definition here. What is enthalpy of formation? That's where you're forming 1 mole of a compound from its elements in their standard states under standard conditions. So if we're forming 1 mole of silver iodide, that's our compound, we're forming it from its elements. So its elements are silver and iodine. Well, what is the formula and the state of silver? Well, it's a metal. Those metals are solid, room temperature, so it's just AgS. It's not going to be the ions, so that rules out C and D. Iodine is diatomic, as all halogens are when they're elements, and iodine is in fact a solid. So silver solid, iodine's a solid. Because the compound is AgI, we need half I2 to make it balance. Question number 10. Some bond enthalpies are given. What's the enthalpy change for this reaction? Relatively straightforward bond enthalpy calculation. Remember to work out enthalpy change using bond enthalpies. You do bonds broken minus your products. So reactants minus products. Only place you may fall down here is the understanding that CO2 has double bonds, but the table gives you C double bond O there. So you've got CH4, always helps to draw the bonds out, plus 2O2. That's our bonds broken. Makes CO2. Remember C double bond O, and you've got 2 of those, and 2 lots of H2O. I'm going to draw out the 2 water molecules. So bonds broken, you've got 4 lots of CH bonds and 2 lots of OO bonds. So 4 lots of CH, or 4 lots of 412, 2 lots of O double bond O, or 2 times 496. So the bonds broken, or the reactants here, are going to give us an enthalpy change of 2,640 kilojoules per mole. C double bond O, we've got 2 C double bond O's there, or 2 times 743. We've got 4 OH bonds in the 2 moles of water. So we've got 4 times OH, or 4 times 463. So add those values together and you get the bonds being made, or the products bond enthalpies, as 3,388. Enthalpy change, bonds broken or reactants minus bonds made or products, will give us our final enthalpy change of minus 698 kilojoules per mole. Answer D. Question number 11. In which conversion is the metal reduced? So reduction is a gain of electrons, or where your oxidation state is reduced, or is gaining electrons, oxidation state is going to become more negative or less positive. So going through the oxidation states of each one of these here. So dichromate, if you've got 7 oxygens, that adds up to minus 14, so each oxygen is minus 2. How do you get from minus 14 to the overall charge? You must add 12. So chromium, well, the 2 chromiums must be plus 12, each chromium is plus 6. In CrO4 minus, each oxygen is minus 2, so you've got minus 8. Minus 8 to minus 2 means the chromium must be plus 6. So there's no redox occurring in that first half equation. When we have B, we've got manganate. the oxidation state in MnO4- is +7. So the manganese is changing oxidation state. It's going from +6 to +7. Oxidation state is increasing, so that manganate there is being oxidized, not reduced. At titanium oxide, it has an oxidation state of +4. The titanium in the products also has an oxidation state of +4. So just like with A, there is no redox. Therefore, hopefully D, we're going to have some reduction. Just go through that one. So vanadium in VO3-, each oxygen is -2. The overall charge is -1. So if each oxygen is -2, that means the vanadium must have an oxidation state of +5. Topic vanadium with a +5 oxidation state is yellow. And then in our product we have VO2+. So if the oxygen is -2, the overall charge is +2. That means the vanadium must have an oxidation state of +4. So remember the vanadium from the transition metals topic, the colour is blue in the +4 oxidation state. So it's going from yellow to blue. It's going from +5 to +4, therefore it's being reduced. Here's our rate expression for the reaction between X and Y. Which statement is correct? So when it says which statement is correct, you do have to work through all of the statements just to make sure you're confident with your answer. So statement A, the rate constant has the units mole -1 dm cubed s to the -1. To work out the units for the rate constant, this is for statement A, you rearrange the rate expression to make K the subject. So K, I'll rewrite that because I wrote that wrong, K equals rate over x squared times y. You plug in the units for concentration and rate. So units for rate is moles per decimeter cubed per second. And then we have 3 lots of concentration. So you've got moles per decimeter cubed squared for x times moles per decimeter cubed for y. Now looking at this, you then simplify the expression, so one of the moles per decimeter cube is going to cancel out. So the units for the rate constant is going to be s to the -1 over moles per decimeter cube squared, or s to the -1 over moles squared dm to the -6, and that can finally be simplified s -1 mole -2 dm plus 6. So they're not the units. Statement B, the rate of reaction is halved if the concentration of X is halved and the concentration of Y is doubled. So what's going to happen to the rate, this is statement B, if X is halved, then the rate is going to divide by 2 squared or divide by 4. If Y is doubled, then the rate will also double because it's first order. So Y doubling will double the rate. X halving will quarter the rate. So what's going to happen to the overall rate if you divide by 4 and then times by 2? Well, overall that means you're halving the rate. So statement B is correct. Let's just eliminate C and D. So C, the rate increases by a factor of 16 if the concentration of X is tripled. And the concentration of Y is doubled. So if X is doubled, if X is tripled, then what's going to happen to the rate? The rate is going to increase by 3 squared or times by 9. If Y is doubled, the rate is also going to double because it's first order. So overall the rate will times by 18 increase by a factor of 16, it would be a factor of 18. So that's incorrect. And the rate constant is never independent of temperature. As temperature increases, the rate increases exponentially, which means the rate constant increases exponentially as well. So that's an incorrect statement. On to question 13. Which statement about pH is correct? So the pH of a weak base is independent of temperature. Just like with weak acids, your weak base pH is determined by the level of dissociation. So for example, ammonia is a weak base and it exists in an equilibrium as seen here. Because it's an equilibrium reaction, it is not independent of temperature. You change the temperature, you change how much dissociation occurs. So that is an incorrect statement. At temperatures above 298 Kelvin, the pH of pure water is less than 7. So the pH of water can be worked out using the Kw expression. In pure water, the statement can be true that H plus concentration equals hydroxide concentration. Because again, in pure water, water dissociates to form hydrogen and hydroxide ions at a 1:1 ratio. So in pure water, because H plus equals OH minus, we can simplify the Kw expression to give us Kw equals H plus squared. Therefore, H plus in pure water is the square root of Kw. Minus log your answer to get the pH. So in pure water, what's happening is you're getting more dissociation at a higher temperature. The bonds are going to be breaking more. Forward reaction is endothermic. So if you're getting more dissociation, you're going to get a higher Kw value and a higher hydrogen ion concentration. So higher hydrogen ion concentration in higher temperatures, or at higher temperatures, will result in a lower pH. So at temperatures above 298 Kelvin, when it gets hotter, there's more dissociation, the pH of pure water is indeed less than 7. So statement B is correct. Let's just go through C and D to eliminate them. So nitric acid, HNO3, is a strong monoprotic acid. So to work out the pH of a strong monoprotic acid, you just minus log the concentration of the acid. So minus log 2 moles per decimeter cubed. That gives us an answer of minus 0.3 as a pH, not 0.3. And finally, statement D, pH of 0.1 moles per decimeter cubed sulfuric acid is greater than 0.1 mole per decimeter cubed hydrochloric acid. So sulfuric acid and hydrochloric acid. Hydrochloric acid is a strong monoprotic acid. So to find the pH, you would do minus log 0.1. You wouldn't have to do this on your calculator, but you could do just to check. So the pH of 0.1 mole per decimeter cubed HCl is 1.00. The pH of sulfuric acid, so if the concentration is 0.1, it's diprotic. So therefore there would be twice as many hydrogen ions. So you'd have to minus log 0.1 times 2. So that will give you a pH of 0.7. Again, for every 1 mole of sulfuric acid, you would get 2 moles of H plus ions. So the concentration has to be doubled before you minus log your answer. So the pH of sulfuric acid would be less than that of hydrochloric acid. That's why that statement is incorrect. Question 14, staying on the acid-base topic. So you've got an acid slowly added to a base, which has the highest pH at the equivalence point. So this is knowledge of your different pH curves. So we're adding the acid to the base. So we're going to be starting at a basic pH. Remember, pH is on the y-axis. And you're adding the volume of acid incrementally. So for combination of A, you have a weak acid and a strong base. So your pH is going to start high because it's a strong base, and then it's going to finish off at around pH 3, depending on the concentration. You could work that out. But the equivalence point, the pH is going to be greater than 7. Probably around 9 or so. So the pH would have a high equivalence point. For B, we have a weak acid and a weak base. If you've got a weak acid, weak base, you don't actually have an equivalence point. There's no vertical section. For C, we have a strong acid and a strong base. So you get a very large vertical section with the equivalence point at pH 7. And finally, for combination D, you have a strong acid and a weak base. So your equivalence point is going to be less than 7. Probably around pH 5 or thereabouts. So which one will have the highest pH at the equivalence point? It is the combination of a weak acid and a strong base. A is correct. On to question 15. In the test for a halide ion in aqueous solution, dilute nitric acid is added before the addition of silver nitrate. Why is nitric acid added? So it increases the concentration of nitrate ions. Well, the concentration of nitrate ions increasing has no effect on the precipitate. Nitrate ions, when they form compounds, are always soluble. So that's irrelevant in this question. Similarly, let's just have a quick look at statement C. Adding nitric acid prevents the silver nitrate being precipitated. Well, silver nitrate, again, it contains nitrate ions. Silver nitrate is always soluble. So that statement's irrelevant. And statement D, it provides the acidic solution required for precipitation. We don't actually need a solution to be acidic for precipitation to occur. For example, if you had barium ions and you added carbonate ions, you would get a barium carbonate precipitate in the absence of acid. So you don't need an acidic solution for precipitation. Statement B is the correct answer. So when you add an acid, it provides hydrogen ions. The hydrogen ions will react with anything that would precipitate with silver. So for example, silver would form a precipitate with hydroxide ions. Silver would also form a precipitate with carbonate ions, which would have these two formula here. So if you've got hydroxide or carbonate ions present in solution, and you're testing for a halide ion without acid, you would get 2 or 1 other precipitate forming. That would mask the halide that's forming the precipitate with silver ions. So therefore acid will react with hydroxide to form water, react with carbonate to form water and carbon dioxide, remove those from the solution, and therefore allow you just to see the precipitation of the halide silver complex. Question 16. Which shows the major products formed when chlorine reacts with cold dilute aqueous sodium hydroxide? So when you've got cold sodium hydroxide, just write out the balanced equation here for you. This is on the specification and is one that you need to learn. It's a disproportionation reaction. You get sodium chloride, sodium chlorate, NaClO or sodium chlorate 1, and water. It's disproportionation because the chlorine with an oxidation state of 0 becomes -1 in sodium chloride and +1 in sodium chlorate. Just as a side note, there's a similar reaction with hot sodium hydroxide instead. But the question's asking you about cold NaOH. If you had hot NaOH, you're going to form sodium chloride and water as before, but you get sodium chlorate 5 instead. Slightly different oxidation state of chlorine there. That's why option D is given. This second equation isn't on the specification, but maybe one you've covered. The first one is one that you need to learn. So C is the correct answer here. Question 17. Which shows the electron configuration of a transition metal. So a transition metal is in the D block of the periodic table. So if these are atoms, we can automatically rule out A, which ends in 4s2, it's in the S block. A is calcium. And we can automatically rule out D, which is in the P block, fourth period, that is gallium, neither of which are transition metals. So transition metals exist in the D block. We've got two transition metals here, two D block elements here. The first one has 28 electrons. It's got 28 electrons, that one is nickel. And we have 30 electrons, and that is zinc. The definition of a transition metal is one which contains an incomplete D subshell as an atom or one of its ions. Remember, zinc only has one common ion, which is Zn2+, so its electron configuration as an atom has a complete D subshell. As an ion, it loses its 4s electrons and ends in 3d10. It still has a complete D subshell. It is not a transition metal. Question 18. Which will not act as a ligand in the formation of a complex ion? So a ligand has a lone pair, donates a lone pair to a transition metal. CH4 is the only one with no lone pair of electrons. It's got 4 bonding pairs. No lone pairs, so that can't be a ligand. B, C and D all have a lone pair and therefore can act as ligands in this case. So they'll be forming ligands by donating their lone pair to the transition metal complex. So again, A is the only one that is not a ligand in this case. Question 19. Which shows the correct oxidation state and coordination number of cobalt in this complex? So notice there are 2 chlorines in the overall formula. Those chloride ions will neutralize the complex. So the fact that we've got 2 chloride ions bonded to the overall complex suggests the complex has an overall charge of 2+. So this is our complex. Now we have 5 ammonias as ligands and 1 chloride as a ligand. So the coordination number is going to be 6. There are 6 ligands bonded. So B or D are correct. Now what's the overall charge of the ligand, of the ligands? Well, ammonia has no charge, chlorine has a -1 charge. What's the overall charge on the complex? it's +2. So what must be the oxidation state of the cobalt? What do you add to -1 to get to the overall charge? You add +3. So the oxidation state of cobalt is +3 because of the chloride ligand here. Question number 20. Which statement is not correct? So CuCl4 2- is square planar. CuCl4 2- is in fact tetrahedral. So that statement is incorrect. You get square planar complexes when you have 4 ligands bonded to platinum, palladium or nickel. Otherwise it's going to be tetrahedral. So again, statement A is incorrect. But when it's saying which statement, you should go through all of them just to make sure you're confident with your answer. So is ammonium tetrahedral? It is, because there are 4 bonding pairs. The extra lone pair on nitrogen forms a dative covalent bond or a coordinate bond with an H+ ion. So that is tetrahedral. Complex C, you've got diaminoethane in there, which is a bidentate ligand. So if you've got a bidentate ligand and you've got 3 of them, you've got a coordination number of 6. There are 6 coordinate bonds, so that is an octahedral complex. So that is a correct statement. And statement D, hexa aqua iron 2 is octahedral. Well, again, there are 6 ligands, coordination number of 6. 6 coordinate bonds formed means it is octahedral. So A is the only incorrect statement there. Question 21. Which compound decolorizes acidified potassium manganate? So manganate is an oxidizing agent. It's purple. It will be decolorized when it is reduced to Mn2+. So we need a reducing agent, or something that would be oxidized by manganate, in order for this conversion to occur. So notice that they all have sulfates in them. So obviously the sulfate is not going to be involved in this reaction. So we're looking at the metal ions that are present. So would aluminium 3+ reduce the manganate? Would copper 2+ reduce the manganate? Iron 2 or Fe2+, or iron 3, Fe3+. So you should know from the redox titrations topic that manganate will react with Fe2+ ions. Manganate will oxidize the Fe2+ ions to Fe3+, and the manganate itself is reduced. So Fe2+ or iron 2 sulfate is the correct answer. Fe3+ is not oxidized any further. Fe3+ is reduced, so that wouldn't also reduce the manganate. Aluminium 3+ is not oxidized or reduced, and copper 2+, its only other common ion is copper 1+. So copper 2+ would also be reduced and not oxidized. So Fe2+, from the redox titration subtopic of the transition metals, is the correct answer. Question 22. Which has EZ isomers? So EZ isomers, the criteria for it to have EZ isomers is you have a carbon-carbon double bond, and each carbon in the double bond will have 2 different groups. So the groups A and B cannot be the same, and E and F cannot be the same for EZ isomers to exist. So you have C2H2Br2. So you've got C2H2Br2. That could exist as 1,1 dibromoethene or 1,2 dibromoethene. So this one will not exist as EZ isomers, but 1,2-dibromoethene could exist as EZ isomers. The one I've drawn is the Z isomer. Let's just go through the others. B, you only have one bromine. So therefore one of the carbons will always have two hydrogens on it. It will not exist as EZ isomers because two of the groups are the same on one of the carbons. C, you've got 4 hydrogens and 2 bromines. So C has too many hydrogens for it to be an alkene. So because it's a haloalkane, it's not got a C double bond C, it won't exist as EZ isomers. So you can have 1,1 dibromoethane or 1,2 dibromoethane. Similarly with compound D, you've got too many hydrogens. So compound D is just bromoethane, no carbon double bond, it won't have EZ isomers. The only one that has EZ isomers is compound A. Question 23. Which is the mechanism for this conversion? So when you're working out a mechanism, you need to look at the groups that are changing. So you've got a methyl group or a CH3 group becoming a haloalkane. So you're breaking a CH bond and you're making a CCl bond. How do you make a haloalkane from an alkane? We need a halogen in the presence of ultraviolet light to break the strong CH bond, and that is free radical substitution. So answer C is correct. Question 24. Which compound decolorizes bromine water in the absence of sunlight? It's a strange phrase, that absence of sunlight. That just means there's no UV light, so we're not going to be forming any bromine radicals. So just standard bromine water, Br2, is going to react or decolorize alkenes or compounds with C double bond C. So it's not going to decolorize a haloalkane, it's not going to react with a benzene ring under normal conditions. C is a cycloalkane, there's no carbon-carbon double bonds. D, might help to draw this out, is indeed an alkane, as we can see from the last 2 carbons there. So you have a CH and you have a CH2, which means that, those last 2 carbons must have a double bond in. Because they've got a double bond, they'll react with bromine water. The bromine water will go from orange to colourless. Question 25. Which compound reacts to form a ketone when warmed with acidified potassium dichromate? So when it reacts with dichromate, it's being oxidized. Dichromate is an oxidizing agent. And to form a ketone, it must be a secondary alcohol. So if you're not sure, draw them out. The A is a primary alcohol. That is propan-1-ol. So that would be oxidized to propanal, which is an aldehyde, or propanoic acid, which is a carboxylic acid. C is an aldehyde, so we'll come back to B in a second. So that is propanal. When it's heated with acidified potassium dichromate, it would become propanoic acid, or carboxylic acid. D is a carboxylic acid, it cannot be oxidized. Now B, you might be looking at that formula a little bit confused. So remember, it has to be a secondary alcohol to be oxidized. So you've got CHOH, and then you've got 2 CH3s. So that's what the formula is. It looks a little bit strange, so I'll just redraw it in a sec. But you've got 3 carbons in a row with an OH on the middle carbon. So propan-2-ol is a secondary alcohol, it would be oxidized to a ketone. It would be oxidized to propanone. So B is the only one that would form a ketone there. Question 26. Which one does not contain an asymmetric carbon? An asymmetric carbon is a chiral carbon, one with 4 different groups attached. So you'd have to look at these, try and work out which one has 4 different carbons, 4 different groups attached. Now it's quite easy to eliminate some of them, because if they have more than one hydrogen on it, it can't be an asymmetric carbon. So going through A, let's draw A out first. It's not going to be any of the ones with the CH2s or the CH3s. So the only possible one that could be asymmetric is this one here. So I'll start by drawing that out. You've got an H and a CH3. You've got a CH2 CH3 and you have a CH3 there. So compound A, when I've drawn it out like this, hopefully you can see that these two CH3 groups are on the same carbon. There is no chiral carbon there, no chirality or no asymmetric carbon atom. So A is the correct answer. That's the only one with no chiral carbon. I'll just go through B to D to eliminate those answers as well. So again, it can't be any of the ones with the CH2s or the CH3s. So B, the only one that may be chiral is this one here. So I'll start by drawing out the CH and the CH3 as before. What's to the right of that? You've got 3 carbons in a row, so C3H7. And on the left of that, you have a CH2 CH3 group. There are 4 different groups attached, so B does have a chiral carbon. Compound C, where you have 4 different groups. Again, ignore the ones with the CH2s or CH3s because they can't be chiral. See there are 4 different groups attached, so that one does have chirality, or it does have an asymmetric carbon. And finally, compound D, you've got an H and a Cl, got CH3, and you have a CH2 CH3. So you have 4 different groups attached once again. So A is the only one with no asymmetric carbon. Question 27. Which reaction involves addition-elimination, also known as nucleophilic addition-elimination? This occurs when you have an acyl chloride or acid anhydride. And the 4 reactions you need to know from this topic were it's reactions with ammonia or water, amines or alcohols. So equation B is showing the reaction of an acyl chloride with an alcohol to make an ester and HCl. So B is showing nucleophilic addition-elimination. If you selected A, C or D, I'll just go through those to highlight what the mechanism is. So in A, you're adding hydroxide to a haloalkane to make an alkene. A is base elimination. C, you have an alkene plus a halogen to make a dihaloalkane. The mechanism for alkenes is electrophilic addition. And finally, D, you have a haloalkane plus a hydroxide to make an alcohol. That one is nucleophilic substitution. Question 28. Which compound reacts with hydrogen bromide to give 2-bromo-3-methylbutane as the major product? So I'll start just by drawing out 2-bromo-3-methylbutane. So you're going to have your bromine on carbon 2, methyl on carbon 3. So this one is your 2-bromo-3-methylbutane. You'll notice that they're given as condensed structural formulae, so I'll just write these out using that formula as well, just so we can see. So you have CH3 CHBr, CH, and then you have two CH3s on this carbon here. So I'm just sticking to the formats given in the question, so CH3, 2. So when you add a hydrogen halide to an alkene, the rule is, it's known as Markovnikov's rule, is the hydrogen will attach the carbon with the most hydrogens on it already in the double bond. So in A, an H and a Br are going to join onto these two carbons here. The H will join on the right carbon because that's got one hydrogen on it. So the product would be CH3, 2. C, the Br will join on that carbon. The H will join on the one with the hydrogen on it already, CH3. B, the major product is going to be formed when the hydrogen joins onto the right hand carbon, or the far carbon, because that's got two hydrogens on, whereas the one on the left only has one hydrogen on. So you'd get CH3, two lots of CH2s, CHBr, so that's where the Br joins on, and then CH3. Again, C, I'll just go through this. You've got your hydrogen joining on the right carbon, and your Br is going to join onto this carbon. So you'd get CH3, CH2, CBr with a CH3 coming off it, and then a CH3 at the end. And finally D, you're going to have your hydrogen join on here and your bromine join on here. So that will give you your major product as CH3, 2, CH, CHBr, and then CH3. So again, the reason the major product forms is based on Markovnikov's rule, and it's to do with the stability of the carbocation that forms in the mechanism. So which one is 2-bromo-3-methyl-butane? It is in fact this one here. It's the same formula, just written backwards. And that's because it forms a more stable carbocation than if the H was to join here. Question 29. Which one's going to form a polymer with a diacyl chloride? Well, diacyl chlorides or dicarboxylic acids will react with diamines to form polyamides, or diols, two alkyl groups, to form polyesters. So A has got your two amine groups that will form our polyamide, So this one will form a polymer. A is correct, and we'll just go through B, C and D. B is an acid anhydride. So acid anhydrides, acyl chlorides don't react together. C is an amide, again, that's not going to react with a diacyl chloride. And D has an amine group and a carboxylic acid group. The carboxylic acid group will not react, but the amine group will. So D is in fact an amino acid. You will get a reaction, but it won't form a polymer. It will just form an amide instead. Again, A is the only one that's going to form a polymer with a diacyl chloride. Question number 30. Which structure shows a zwitterion of an amino acid? So a zwitterion then is going to be one with no overall charge, and it happens as the COH of one amino acid donates its proton, and the NH2 of another amino acid accepts a proton. So you're going to have no overall charge with a CO- group and an NH3 plus group. It can't be A because there's two positive charges. Similarly, it can't be B because there are two negative charges. C is not the correct formula for a zwitterion because you don't have the NH3 plus, and therefore D, apologies I've cut this off here, has an NH3 plus and a COO minus there. So D is the only formula for a Zwitter ion. Question 31. What's the minimum volume in centimetres cubed of potassium manganate? And you're given the concentration there needed to oxidise 0.01 moles of VO2+. So you have 0.01 moles of VO2+. So how many moles of manganate? Well, it's a 5:1 ratio, so we need to divide the moles by 5. Therefore the moles of manganate, again 5:1 ratio, is 0.002 moles. We've got the concentration of potassium manganate, we've now got the moles of potassium manganate. We're being asked to calculate the volume. So volume is moles divided by concentration. So 0.002 moles we've just worked out, divided by the concentration that's given to you, will give you an answer of 0.1 decimeters cubed. Question saying what's the volume in centimeters cubed, so 0.1 decimeters cubed is 100 centimeters cubed. Question 32. What's the concentration of sodium hydroxide in moles per decimeter cubed that has a pH of 14.3? You're given the Kw value. So because sodium hydroxide is a strong base, fully dissociates in solution. So if you have whatever the concentration of hydroxide is, which we're going to work out in a minute, you'll be able to work out the concentration of NaOH because it's a 1:1 ratio. So firstly, if you're given the pH, you can find the hydrogen ion concentration by doing 10 to the minus pH. So 10 to the minus 14.3 is going to give us the H plus concentration of 5.0118 times 10 to the minus 15 moles per decimeter cubed. What other information do we have that's going to allow us to calculate the concentration? Well, it's the Kw value. So to find the concentration of hydroxide, what's the expression for Kw? Rearrange to make OH minus the subject. So Kw divided by hydrogen ion concentration. So our hydroxide concentration then is 5.0118 times 10 to the minus 15. So I've done that the wrong way around. The value of Kw, which is 10 to the minus 14, or 1 times 10 to the minus 14, divided by the concentration of H+, which gives us our concentration as 1.995 moles per decimeter cubed. Rounded up, that's going to be 2.00. Answer D is correct. Question 33. What are the units of the rate constant for a third order reaction? So we looked at calculating units for a rate constant back in question 12 it was. So if it's a third order reaction, I'll go through step by step how to calculate it. It doesn't matter if you've got 3 reactants or if it's just A to the power of 3. But you've got 3 concentrations, third order overall. So in order to work out the units for rate constant, you make K the subject. So K equals rate divided by our 3 reactants or 2 reactants, whatever it is, as long as you have 3 concentrations in there. Substitute in the units. So units for rate, moles per decimeter cubed per second. Units for concentration is moles per decimeter cubed. And we've got that 3 times. I'll just write out each one just to show how to calculate it if you're not too sure with this bit. So let's simplify this fraction. We've got 1 moles per decimeter cubed on the top, so that cancels out with 1 moles per decimeter cubed below. That leaves us with S to the minus 1 on the top and 2 lots of moles per decimeter cubed. Simplify that. S to the minus 1 over 2 lots of moles and dm to the minus 3 squared, or dm to the minus 6. Because it's on the bottom of the fraction, that's further simplified to S minus 1 mole minus 2. You get the inverse if it's on the bottom of the fraction, and dm to the plus 6. Neaten that up, normally you put the negative powers later on in the units. So we have moles minus 2, dm6, s to the minus 1. D is correct there. Question 34. What's the pH of 0.015 moles per decimeter cubed of sulfuric acid? So remember, this is a strong acid, it fully dissociates. It's also a diprotic acid. So if you got this question wrong, it may be because you forgot that bit of information there. So if you've got 0.015 moles per decimeter cubed of sulfuric acid, how many moles of hydrogen ions are you going to have? We have to times it by 2, 0.03 moles per decimeter cubed. So if that's the concentration of H+, how do you find the pH? You minus log your answer. So minus log 0.03 will give us our final pH there of 1.52. C is the correct answer. Which compound is formed when phenyl benzene carboxylate is hydrolyzed under acidic conditions? So this is an ester. You've got your carboxylic acid on the right of the name and your alcohol on the left of the name. Benzene carboxylate, you have a benzene ring, C double bond O and O. That would be OH if it's the carboxylic acid. And the phenyl group is from phenol. So you have a benzene ring with your O there. So looking at the formula for benzene, phenyl benzene carboxylate, C6H5, COO, C6H5. When it's hydrolyzed under acidic conditions, reversible reaction, it's going to form benzene carboxylic acid, which has this formula, and it's going to form phenol, C6H5OH. So which one is correct here? It's going to be answer D. Question 36. Student rinsed the apparatus before starting an acid-base titration. The results of a titration showed that the volume of acid from the burette was larger than expected. So we're adding too much acid from the burette, more than we'd expect. So here's my burette, I've got acid in there. Why is the volume too large? So go through the statements. The conical flask was rinsed with water before the titration. Well, even if you add a little bit of water in here, you're still going to have the same moles of alkali, and therefore you're going to have the same moles of acid being added. So rinsing the conical flask with water at any point will not affect the titer. The walls of the conical flask were rinsed with water during the titration. So again, that's actually a good practical technique to do. If you get a little bit of acid, so that's my deionized water bottle, if you get a little bit of acid on the sides, you can rinse it with water to ensure that all of the reactants mix together. So B is incorrect as well. Sorry, I put a cross in A, I meant a cross for it being wrong. If the pipette was rinsed with water, so the pipette is going to have our base in it. If our pipette's rinsed with water, then we're going to have more dilute base. If it's more dilute, there's less moles. So that would result in less volume of acid being added from the burette. Not more volume, which is what the question's asking. So C is incorrect as well. And finally, statement D, the burette was rinsed with water. So if I rinse the burette with water, that's going to dilute the acid, or the concentration of acid is going to go down. So to make sure I've got the same moles of acid reacting with the base, I'm going to need a greater volume of the acid. The volume from the burette is larger than expected. So statement D is correct there. And I can correctly cross that in row D there. So that brings me to the end of the recording for the Paper 3 2020. If you'd like further clarification on any of the questions, then please do add a comment below and I'll I'll get back to you when I can. Otherwise, best of luck with your exams.